Oscillating springs and other naturally occurring phenomena can be modeled by combining trigonometric functions with algebraic functions. Hi, my name is Tom Atwater, and in today's lesson, we will be investigating composite trigonometric functions. Let's start by looking at some examples of how algebraic functions can affect trigonometric functions and their graphs. So, what we have is graph each of the following functions for negative 2 pi is less than or equal to x, which is less than or equal to 2 pi, adjusting the vertical window as needed. Which of the functions appear to be periodic? So we have 4 that we're going to investigate, and I won't read them on this screen because I'll read them on their individual screens. But those are the 4 that we will look at. So the first one, part A, y equals sine x plus x squared. And here's what that graph turns out to look like. So you can see that adding x squared really changes the look of sine x. All right, in this particular case, it's not periodic if we look at it as you would think with sine x is. Now the effect is that it's not. All right, let's look at part B. Part B, y equals x squared times sine x. And here's the graph that you get when you enter that into the grapher. Again, it's a little bit similar to sine x, at least more so than our last graph, but again, the x squared greatly affects it because what happens is these graphs continue off into their own, and therefore this also is not periodic. All right, what about part C? Part C, y equals sine of x, the whole thing squared. Well, of course, it does make sense. When we square it, it becomes positive, so we don't see anything below the x-axis. And in this case, we can see that it appears to be periodic still. And finally, y equals sine of x squared. And this is different than the one we just did because in this case, we are only squaring the x value, and therefore we will get negative values from here. And this particular one, when we look at it close into the y-axis, it's staying above it, but then as you see we go further out, it does go below the x-axis, and that one is not periodic. Well, let's take a specific example, and we have verify algebraically that f of x is equal to the sine of x quantity squared is periodic, and determine its period graphically. Okay, so in this particular case, we have sine of x, the original sine of x, and we're going to take that and square it. Now, we're going to use the fact that the period of the basic sine curve is simply 2 pi. And we also know that we can take the sine of x plus 2 pi and say that that's equal to the sine of x for all x. Now what we can do is plug x plus 2 pi into f of x. So in other words, we'd have f of x plus 2 pi, and so that would be equal to the sine of x plus 2 pi, and then the whole thing squared. However, we've already said that the sine of x plus 2 pi is equal to the sine of x. So what we can say is f of x plus 2 pi is equal to the sine of x, but then again, the whole thing squared. And now I can use the fact that up here, we've said that the sine of x squared is equal to f of x. So that means f of x plus 2 pi is equal to f of x. And therefore, we can conclude that f of x is periodic with some period that divides into 2 pi. Now, we saw the graph a moment ago, but I'd like to show it to you again. And that's the graph of f of x equals sine x quantity squared. You can see that it's clearly periodic. In this particular case, we observe that the period is pi. Well, now let's work an example in which we add a sinusoid to a linear function. The graph of f of x equals 0.5x plus sine x oscillates between two parallel lines as seen in the following graph. What are the equations of the two lines? And here's the graph where we see it oscillating in between those two red dotted lines. And we want to try to figure out what the equations for those lines are. So let's take a look algebraically. We have f of x equals half of x plus sine x. Now what we know is that sine x oscillates between 1 and negative 1. So therefore, f of x would oscillate between half of x plus 1 and would be negative, 0.5x minus 1, because that's where the sine of x is oscillating between. So therefore, what we have is that it's oscillating between y equals 0.5x plus 1 and y equals 0.5x minus 1. So those are the equations of the two lines that graph is oscillating between. Let's look at the rules for the sums that are sinusoids. So what we have is this. If y sub 1 is equal to a sub 1 times sine of b times the quantity x minus h sub 1, and y sub 2 is equal to a sub 2 times the cosine of b times the quantity x minus h sub 2, then adding together y1 plus y2 would be equal to a sub 1 times the sine of b quantity x minus h sub 1 plus a sub 2 times cosine of b quantity x minus h sub 2 is a sinusoid with a period of 2 pi over b. Let's do an example. Let's determine whether each of the following functions is or is not a sinusoid. And in order to do that, we say that if the sum is going to be a sinusoid, then the sinusoids being added together must have the same period. Here we have our first two examples. So we're going to determine whether the following functions are or are not a sinusoid. So the first one, f of x equals 5 cosine x plus 3 sine x, they do have the same period. It's 2 pi. Therefore, A is yes, that is. What about B? Well, if we look at these are not going to have the same period. And therefore, the answer to this is no. And we can specifically say that the period for this one is 2 pi over 5, whereas the period for this is 2 pi over 3. I have two more examples. And part C, we can look and say, okay, they will have different periods. This one would have a period of 2 pi over 3. That would have a period of 2 pi over 2, or in other words, pi. And therefore, the answer to part C is no. What about part D? Well, if we look at this carefully, we'll notice that each coefficient is actually 3/7. And therefore, they are going to have the same period, which would be 2 pi divided by 3/7. 7/7. And that means that the period is 14 pi over 3, and therefore the answer is yes, they are in fact, or that f of x is in fact a sinusoid. Well, now let's turn our attention to something called damped oscillation. The graph of y equals f of x times cosine bx, or y equals f of x times sine bx, oscillates between the graphs of y equals f of x and y equals negative f of x. When this reduces the amplitude of the wave, it is called damped oscillation. The factor f of x is called the damping factor. Let's take a look at an example of this. For each of the following functions, determine if the graph shows damped oscillation. If it does, identify the damping factor and tell where the damping occurs. So we have f of x equals 2 to the negative x times sine 4x. Then we have f of x equals 3 times cosine 2x. And then finally we have f of x equals negative 2x cosine 2x. Let's take a look at each of these functions and their graphs individually. So let's start with A, which was f of x equals 2 to the negative x times sine 4x. Well, as we look at this, we can see that what's happening is, in fact, damped oscillation. The dampening factor is 2 to the negative x. And the damping occurs as x goes to infinity. All right, so that was part A. Let's take a look at part B. F of x equals 3 cosine of 2x. Well, as you can see here, there's no dampening going on. It's not damped oscillation because it's staying at the same height as it goes out. And therefore, we actually can say that it has a constant amplitude. In this case, it's an amplitude of 3. And part C says f of x equals negative 2x times the cosine of 2x. Now, this is interesting because, in fact, as we come this way, let me use a different color. As we come this way, you can see that what's happening is it is, in fact, damped oscillation. And if we go this way, it's damped oscillation. So, in fact, the damping factor is negative 2x, and the damping occurs as x goes to 0. All right, well, you know what? Now it's time for you to try a problem. For the function f of x is equal to e to the negative x times sine 3x, determine if the graph shows damped oscillation. If it does, identify the damping factor and tell where the damping occurs. Pause the video while you work on this problem, and when you're finished, restart the video to check your solution. Welcome back. Let's find out how you did on this. We would plug this into our grapher, graph it, and notice that, yes, in fact, it is damped oscillation. The damping factor is e to the negative x, and it's damped as x goes to infinity. All right. I hope that's the answer that you got. It was similar to a previous example that we've done. So in this lesson, we explored the graphs of composite trigonometric functions. Be sure to work the exercises that your teacher assigns, and we'll see you next time.